Hundreds of years ago, my great-great-great-great-uncle Isaac Newton took a prism like this one in his hands, and when he twisted it, and he shot light through it in one direction, and when he twisted it, he could twist the colors right out of the white light. And he was telling people, see, the white light is composed of a rainbow of colors. But the current theories disagreed with Isaac Newton's fact-finding that white light was made of colors. They said that the prism produced the colors, and that the prism was actually manufacturing the colors. But Isaac Newton knew better. He said, no, see, I can do this simple experiment. I can take this prism, and when I twist it in my hands, the colors will pop out. Prismatic balls that you can hang in a window, and then if the sunlight hits it down a dark hallway, you'll see all the rainbows down the dark hallway. And yeah, just hang this in like a window and have this when the sun hits it through a window, and then you can see many rainbows in your house. Anyway, back to the prism. This thing only has a few facets on it, unlike the other one. Isaac Newton, it was a large point of controversy for the college, because he almost quit the college after that, because his colleagues wouldn't accept that white light was composed of many colors. Instead, they still believed, like the textbooks said, that prisms produce the colors, and that the white light shines through the prism and the prism produces the colors, rather than that the prism twisted the colors out of the white light. But it was a very simple experiment that my great-great-great-uncle did, Isaac Newton. I'm going to do another simple experiment, and this is the first video in the series, Experiments That Will Change the World. People believe the atoms are made up of electrons, protons, and neutrons. And if you were to draw an atom, you'd have the nucleus in the center, and you would have the electrons spinning around the outside. In fact, you've probably all seen the Big Bang Theory show, where they show a lot of electrons orbiting a nucleus. In fact, the standard nuclear symbol looks similar to this. But that's not like what it is at all. Electrons do not orbit a nucleus. They are stable. And in fact, electrons and protons and neutrons, and neutron is just a proton with an electron joined to it. Anyway, all of those parts, they're all just dust. I mean, you're not going to believe this, but not initially perhaps, but the Bible's right that everything is made of dust. In Genesis, in the Bible, God said that everything was made of dust. Now, I can prove that. Because we used to consider that in the atom you have electrons and protons and neutrons, and of course the protons are very, very, very much larger than the teeny tiny electron, and you can't even, it's equivalent to something like the proton is the sun and the electron is the earth. It's a very large size difference. But of course, for the nuclear symbol, you wouldn't be able to see the electrons if this was the size of the nucleus here, with all the protons in it and the neutrons in it, all lumped together. You wouldn't be able to see the electrons. They would be so very, very small on the outsides. But this is basically the nuclear symbol, and that's not how it is. And yes, we see this commonly in culture too. Not only is it is it considered the nuclear symbol, which shows the electrons orbiting the nucleus, it's also in popular culture for being science. But it's not science. It's not, well, it is human understanding, and science is human understanding. But human understanding is often flawed, because we don't understand everything. This is also seen in The Big Bang Theory, the popular TV show The Big Bang Theory, this symbol of electrons orbiting a nucleus. So this is not an uncommon thing. It's also even in pop culture. But it's not true. Electrons do not orbit a nucleus unless they're loose enough and unless they're towards the outside of the atom. They have to be in the outermost shell of the atom in order to orbit the nucleus. Otherwise, they're too tightly compact towards the nucleus. And most of them, even so, must not orbit, because if they did, the crystal structure would fall apart. Let's look at some crystal structures, and I'll show you what I'm talking about. So here are some atoms. Here's the book I'm looking at here. Okay, there's the book, Rocks and Minerals. And there's some very interesting crystal structures in here, as you can see. We've got, and you can see that the shapes directly correspond, the shapes of the crystals directly correspond to the atom arrangements, that is, the arrangements in the crystal. They got pages and pages of the structures of crystals. So many. Here you can see an atomic arrangement there. Various atoms spaced and grouped. And it says, even says in the book, space grouping of atoms, the visible expression of which is the crystal. And so we see that the atoms are spaced and grouped to make a particular crystal form. In fact, that's what all crystals are. But the binding between the atoms are the outermost electrons. So all that's binding between the atoms is shared electrons between these atoms. So, can we prove that all electrons do not orbit around the nucleus? Well, yes, we can. Because here's another book. Yep. Electricity and Electronics. And it's an introduction to it. Here, right on this page here, I'll zoom in. when it says each electron not only rotates around the nucleus of an atom, but also spins on its own axis, this is not the case. Each electron, there's actually only one electron in iron per atom that takes what do you call it? That's involved in the magnetic process. Here is a very nice piece of fool's gold, and it's huge, as you can see. There's my hand there, and there's the fool's gold there. So don't get excited, it's not actually gold. Now, okay, so here's a magnet, and here's an iron ball, and as you can see, the iron ball sticks to the magnet. I can pick the iron ball right up out of my hand with the magnet. Now, here's an even stronger neodymium magnet, and it also sticks to the iron, as you can see. And to demonstrate that it's not that this iron ball is a magnet, but rather that this is a magnet and this is a magnet, I'm just going to demonstrate that yes, indeed, they will also stick to each other. Okay, so we see what's a magnet, what's not a magnet. Now, this is the experiment that's going to change the world, and just like my ancestor, well, my great-great-great-great-great-uncle, Isaac Newton did, I'm about to do an experiment that should change the world. See, this piece of fool's gold is made up of iron and sulfur in crystal form. So, it should, according to the current theories of today, this beautiful piece of fool's gold should stick. Boy, it's heavy. It's heavy because it's mostly iron. It's a large chunk of iron, but it's beautiful, and you can see the crystals in it. And it's mostly iron and sulfur mixed. And the only thing combining between the sulfur and the iron atoms is the electrons, the outermost electrons between the sulfur and the iron. Iron is normally highly magnetic, just like this little iron ball. But, and you can see this powerful neodymium magnet sticks to it. But, this iron is different from this iron because this iron is bonded with sulfur. Let's take this magnet and see if it sticks to this crystal. Nope, not even a little. I can go like this. It won't stick to this iron, this large chunk of iron. As you can see. Alright, we'll try the other magnet. Here's the other magnet. Again, it doesn't stick to the magnet at all. Not even a little. Not anywhere. Okay, so why does that experiment change the whole world of understanding of science? Because the sulfur is bonded to the iron by its outermost electrons. And those electrons. There are 2 electrons in iron that are the outermost electrons. There's just 2. And those 2 electrons, one of them rises up and bonds between atoms in iron. So like, for example, in this ball here, I know this crystal's nice to look at, but I gotta move it. Okay. In this ball here of iron, there is... Actually, I should probably show you the crystal form. Okay. Here's the crystal form for nickel iron. There it is. Nickel iron. And as you can see, it's an octahedron. This octahedron shape here for nickel iron. Now, nickel iron crystals are magnetic, unlike iron sulfur crystals, which are not magnetic, as we just demonstrated in the magnet not sticking to the fool's gold. When you have an octahedron shape, you have 1 electron here, 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 and 1 electron on the other side that you can't see over here. That's 1, 2, 3, 4, 5, 6 electrons. The bonding in iron looks like this. Here, I'll move that up there. Okay. Well, I'm not going to be able to show it all, but... Okay. So, when this atom here each one of these octahedrons represents a single atom of iron. So, and each one of these points on the octahedron in this shape on this crystal is only using 1 electron, just 1 electron per atom, and this is important, 1 electron per atom to bond between atoms. So like, for example, you could say that the electron that this atom right here uses is here. The electron that this atom, that belongs to this atom, is right here. The electron that belongs to this atom here is right here. The electron that belongs to this atom is right here. But you see that they're sharing outer electrons, and you can see that all of these electrons here are in fixed points, not orbiting their nucleus, but stuck in this crystal shape. So here you have this electron stuck here, this electron is stuck here from this atom, this electron here is stuck from this atom, and this electron here is stuck from this atom. And of course there are more octahedrons on top of this, like here, here. Anyway, if you analyze this whole thing, you'll find out that none of these electrons can orbit the nucleus, because if it did, this iron would fall apart. In fact, you can make iron fall apart. The atoms go completely loose and become non-crystallized if you run enough electricity through the iron. If you run enough electricity through the iron, what will happen is these electrons will flow away and be removed, and the atoms will get very, very loose. It'll glow red and then white, and then it will turn into something that looks like lava. And so you run enough electricity through here and you will break all of these little bonds, and the crystal structure will not hold together. And when you move these electrons out, you will indeed and in fact cause it to become lava and no longer a crystal, a structure of iron that we see in iron. Like here it's an iron magnet. This would not, you could melt this iron magnet in and just turn it into lava by running enough electricity through it. So we see that only one electron per atom is needed to bond between atoms in the crystal structure of iron. So, but there's an issue there, because there's actually two outer electrons in iron, not just one outer electron in iron. So what's going on with the second electron in iron? Why is iron one of those rare elements that are actually magnetic compared to so many other atoms out there that are not magnetic? And the reason is because that other free electron, that other outer electron, here, I'll blow up the atom of iron in the crystal shape. Okay, that drawing's not exactly beautiful, but there it goes. Okay, so yes, this would be the bonding between atoms. But here's a single atom of iron, and if it was a single atom of iron, then you wouldn't have the bonding between atoms, because it would just be one atom. But say that this is an atom in the crystal structure, so that it does share electrons on the outer, but it contributes one extra electron out here. What's happening underneath is that there is a bulge, a whole bunch of electrons, about 14 electrons underneath. Well, here's the nucleus in the center, and then you've got about 14 electrons in the next shell underneath. And so you got a bunch of electrons in here, in this area. Sorry about the drawing. Okay. Now, you got your nucleus here, and you've got your electrons, inner shell electrons, and the next shell, and until you finally got the 14 electrons in here, and then you've got 2 electrons on the outside. One of the electrons is up here, and one is doing, wait, what's the other one doing? Oh, it's free underneath this shell, underneath this crystal structure, to actually roll around these other electrons that are in the second most inner shell. And these electrons are so far in, they're stuck. And they're stuck. So this little ball here, which is actually what it is, because why? Because electrons are just dust. Just like everything else is just dust clumps. Anyway, I would have to explain why the apparent attraction between the nucleus and the electrons, but I am not going to do that in this video. Here, the electron it whips around the nucleus. It is actually able to orbit inside this crystal structure, which explains why crystals are able to hold together, and still why a single electron per atom is still able to orbit around its nucleus in order to create the magnetic effect. And that's why the iron can be magnetized, and so many other atoms cannot be. But if this atom, is bonded with, this atom here is bonded with sulfur, as it is with this rock here, here's iron bonded with sulfur, it is not going to stick to a magnet, because this electron here is no longer free to whip around the nucleus. Why? Because it rises up and bonds between, and this electron and this electron here would then be tied to the sulfur atoms between them. And so when these two electrons are tied up in the crystal structure, the iron is no longer magnetic. And that's why this will not stick to a magnet. So this book here, which talked about, you know, this textbook here, which talked about how the magnet worked, doesn't know how the magnet works. And just like my great Uncle Isaac Newton, who demonstrated by simply twisting a prism that the current beliefs weren't true. So I too did a simple experiment. Took a piece of fool's gold, took a magnet, and said, nope, the current theories are wrong again. That what you see on popular TV shows and in science, where they talk about, like for example, the Big Bang Theory shows and the nuclear symbol shows the electrons orbiting the nucleus. This is not the case. This doesn't happen. It only happens in very rare situations where the crystal structure allows for an orbiting electron. Otherwise, the electrons do not orbit the nucleus. They're stuck in crystal forms. Oh yes, they'll vibrate, and oh yes, you can run electricity through it, and this electron will bump out this electron and take its place and all that, all the way down the crystal. But they will not orbit the nucleus, because if you take electricity and run it through the iron, you can actually melt the iron and everything falls apart. So if you move these electrons, you will know it, because you will have a pile of lava. I had a lot of points to demonstrate, and I actually have very many more to show you how the whole universe is just made of dust. That orbiting does not happen except under very special circumstances. Alright, thanks for watching, and have a good day.